This is part 11 of the Module 11 lectures. And in this section, we're going to talk about verifying assumptions in regression analysis. And unfortunately, this is not in the textbook. The author kind of mentioned something about it, but it never really addresses this issue. And this is a very, very important aspect because any inference that you make about the regression model, it relies on this assumption. Remember when we tested the hypothesis for the slope parameter, and when we constructed the confidence interval for the slope parameter, said, well, assuming that the residuals are independent, normally distributed with mean zero and constant standard deviation, and because we estimate the standard deviation with the standard deviation of the residuals, then we use the t-distribution. So if you recall that, we kept on saying that given those assumptions, we can make all that inference. And another inference, or another assumption behind the scenes is that the model is correct. In other words, that there is a linear relationship between x and y. So we need to validate these assumptions before we accept the results of our regression analysis. So as I mentioned in the previous slide, any statistical inference about the slope parameters and the model predictions rely on these assumptions. And so these assumptions must be verified to ensure that we're meeting them. So now you say, well, how can I do that if I do not know the random errors? We do not know the random errors, but we're going to use their estimates, which are the residuals. And we're going to verify this assumption using 4 graphs of the residuals. So the first graph is to validate independence. In that graph, we plot the residuals versus the order in which the data was obtained. If we see that those exhibit a random pattern, that indicates that the residuals appear to be independent. Now, to validate the constant standard deviation assumption, we plot the residuals versus the predicted values. And what we're looking for is for a random pattern of points across all the predicted values, indicating that the standard deviation is constant. To verify normality, we're going to use a new graph called the normal quantile plot of the residuals. And in here, if the residuals follow a straight line, that indicates that they are normally distributed. And to validate the linear relationship, we're going to plot the residuals versus the x values to see if there is a pattern that indicates that there is the relationship between y and x is not linear. All right, so and these graphs are called the residual diagnostic plots. And when you construct the graphs of the residuals versus order versus predicted values and versus the x values, you expect those graphs to show a random pattern. So a band of random points that don't show you any particular pattern. And then the assumptions, if you see that the random pattern, then you say that the assumption of independence in the graph of the residuals versus order is validated. If you see that pattern in the graph of residuals versus predicted values, then you say that the constant variance assumptions is validated. And if you see the same similar band of pattern of points that is random, when you plot the residuals versus the x values, that then validates the assumption of the linear relationship. And there might be situations when these graphs exhibit non-random patterns. For example, and this is just a sample of possible patterns that violate the assumptions. For example, when you have when you see the residuals increasing as they are collected as the order of collection, then you see that these residuals seem to be dependent, not independent. If you see this megaphone pattern of the residuals versus the predicted values, it's telling you that the variance increases as you predict larger values of y. Or you can have the opposite, that the variance is bigger as you predict smaller values of y, for example. Or when you plot the residuals versus the x variable, if you see this curve in the residuals, that tells you that x and y, the dependency of y on x is not linear. So we're always looking for these patterns to see if there's any issues with the assumptions. Now, if you construct a normal probability plot of the residuals, you would expect them to follow a straight line. And if they do follow a straight line, that is an indication that the residuals are normally distributed. Because the way we construct this normal quantile plot is by finding the quantiles that corresponds to these residuals and the normal quantiles. So we're relying on the normal distribution to find the quantiles. And if they match, that indicates that residuals follow a normal distribution. However, if you see these unusual patterns of the residuals in the normal probability plot, they're telling you that these residuals are not normally distributed. All right, so let's look at an example. So we want to validate the assumptions for the example that we've been working with of the hours, the relationship between GPA and hours worked per week. And we want to produce these residual plots using Excel. All right, if you use Excel, remember that you need to have this data analysis tool pack installed. Once you install it, then just go ahead and open the worksheet. Then click on the data tab at the top, and then click on data analysis. And then once this window opens right here at the bottom, find the regression, click on it, click OK, and then you populate this this window as shown here. When you enter the range of the y values, the range of the x values, you click on the labels box, the confidence level, and change the confidence level if it is different from 95. And now the new thing we're going to do here for the residual plots, then click on residuals, click on residual plots and line plots. Do not click on the standardized residuals. Unfortunately, Excel is not standardizing the residuals properly. And using the graphs of standardized residuals will be misleading. Also, the normal probability plot that Excel generates is not the normal probability plot of the residuals, but rather of the response variable, the GPA in this case. All right, once you click on these boxes, click OK. Then Excel, in addition to producing the output for the regression analysis, it produces this table, where it gives you the observation values, the predicted values, and the residuals. And it gives you these two graphs. This is the graph of residuals versus the x value. This is the one it used to verify the linear relationship. And it produces a graph where it compares the predicted values with the observed values of GPA in this case. All right, but from these graphs, the only one that is useful is here. For that reason, I created my own graphs, as I show you in a moment. All right, but let's review this graphs. Well, let me just go here and go to Excel and show you the graphs. All right, so what I did in Excel, here's the original data, and I calculated the predicted values directly using the sample regression equations. Here is B and here is A, and you can click here and see what I did. And so here's A, and I'm using the dollar signs so that I tell Excel to always go back to this cell. And the same for the slope. I said always go to that cell and then multiply by the x value. And once I do that, then I click on this lower right corner and drag the formula down. As I do that, it's going to be doing these calculations for each x value, keeping these two values constant. And then for the residuals, I just subtract the observed GPA minus the predicted GPA. And that's how I get those values. And then to get the normal probability plot, I take the residuals right here, I copy them, pasted them here, and I order them from smallest to largest. Then I add the ranks from 1 to the last value, and then I calculated the cumulative percent of values. We kind of did this in module 4, but I never talked about doing it in this particular case. So it's just the rank minus 0.5 divided by the number of values. And so you do that and drag it down, and that gives you the corresponding percentiles. Then you use these percentiles as probabilities and find the corresponding normal quantiles. And then you plot the normal quantiles versus these residuals to get the normal probability plot of the residuals. So if you want to see how these graphs were constructed, click on the graph and you see what columns are being used. So you click on this graph and you see what columns are being used, and here you see this is the original graph from Excel, so it's not showing which columns I use. So I copy this graph from the one that we produced there. All right, so with that in mind, let's go back to here. All right, so verify independence. We cannot verify independence using a residual graph because we're not given the order in which the data was collected. However, they said that this is a random sample. So because this is a random sample, we can make the assumption that the residuals are independent. To verify the constant standard deviation, we use the graph of the residuals versus the predicted values. And you can see that this is more or less a random band of points indicating that the variance seems to be constant for the different predicted values of GPA. So we can say, given the pattern on this graph, that the standard deviation is constant. Then we look at the normal probability plot or the normal quantile plot. And you can see that the points follow a straight line, more or less. But that's good enough for us to say that the residuals seem to be normally distributed. And then we look at the residual graph, or the graph of residuals versus the X variable, the hours worked per week. And again, we see a pattern of points that it seems random. And if we accept that, then we say that the GPA depends linearly on the hours worked per week. You may say, well, I see a pattern like this. Again, remember, we have only 10 points, so it's really hard to see a very specific pattern. But if you say that that's the pattern, then what model would you fit to the data? An answer is a polynomial model to see if that works. And that's more complicated and unfortunately beyond the scope of this course. So, but we can say that this appears like a random pattern and say that the relationship is linear. And in fact, if you compare the graph of predicted values with the values that were observed of GPA, you see that it's a relatively good agreement. So then we can say that the assumptions of regression that are met. Therefore, all the inferences we made about the slope and about the confidence interval for the predicted values are correct. So our analysis is correct. And the student can then rely on this model to see how much his or her GPA will be affected if he decides to, or she decides, depends, if they decide to go from 8 hours per week to 16 hours per week or more hours per week. All right, so I will stop here. In the next recording, we'll look at an example, a full example.